Hi class, we are now on chapter 5.3. This is chemical formulas. So we're going to learn how to actually represent the compounds where I keep saying H2O or H2O2. This is what we're going to learn. So chemical formulas, this is how we represent compounds without writing them out over and over. As you proceed in chemistry and it gets more advanced, we start dealing with huge, big names. And it's easier to write the chemical formula, but you have to learn the rules to write a chemical formula. So compounds have constant composition. We've already covered that. So when you see a chemical formula, that is its fixed composition. That is what that compound is made of. It doesn't tell you how much you have, but that's what exists there. So a chemical formula indicates the elements present in a compound. So think of this as a last name more than a first name, because that last name is associated with you. Doesn't tell you, doesn't say what you look like, doesn't say anything more than that's related to you. So chemical formula indicates the elements present in a compound and the numbers of each atom, numbers of atoms of each. I don't like that. Water, again, is the simplest one. It's one we're all familiar with, so it's one I'm always going to go back to. Water has 2 hydrogens and 1 oxygen, and that's a mole ratio. The formula contains the symbol for each element. If there's a 1, the 1's omitted, so that's why you don't see a 1 with the oxygen. So if we looked at this, symbol for hydrogen is H, symbol for oxygen is O, capital letters. Subscript, this means 2. Subscript, that's lower. That's 2, that means there's 2 hydrogens. And 1 oxygen, there's no 1 here. By default, we don't write it. So when you don't see something, that means it's a 1. In this case, it's not always, unfortunately, as we go through. This is going to get harder. So as of right now, when you don't see a 1, that means 1 atom. Chemical formula. So common ones is sodium chloride. That's a 1-to-1 ratio. Carbon dioxide is a 1-to-2 ratio. 1 carbon, 2 oxygen. Sugar, sucrose. It is a ratio of 12, 22, and 11. That means carbon has 12 atoms, hydrogen has 22, and oxygen has 11. That is what makes up the compound of sugar. The subscripts in a chemical formula represent the relative numbers. Relative meaning how these are all related to each other in this compound. Just like you're related to people, that word relative means they are related to each other in this compound. So for each type of atom, they never change for a given compound. If those subscripts change, you no longer have that compound. You have something else. For instance, again, water is H2O. But if you have H2O2, you do not have water. You don't want to drink hydrogen peroxide. That is hydrogen peroxide. So if a subscript, even 1 subscript changes, it is something else. Okay, so this is a perfect example. We have carbon monoxide and we have carbon dioxide. There's a big difference in them. The subscripts in a chemical formula are part of the compound's definition. So if you change, again, not the same compound. CO is carbon monoxide. That's made of 2 elements, and there's a 1-to-1 ratio. If we have CO2, we now have 1 carbon, but we have 2 oxygens, which means that this is different. It's a 1-to-2 ratio. And these are both gases. One is what they call a silent killer. I don't know if you guys are aware. Every Christmas, unfortunately, if you pay attention to news, there's always a family that has passed away. And it's usually because of carbon monoxide in their house. It's a silent killer. That's why you have to have these detectors in your house. You go to sleep and you don't wake up. You just become groggy, and it's very dangerous. And it usually has to do with their heaters or something like, a generator being on without, it's bad. And carbon dioxide is also bad for you, but it's not the same bad as carbon monoxide, even though both of them, it's what we exhale, but you do need to have oxygen in the room. You don't want to keep breathing CO2. How to list the elements in order of compounds. So how do we list this? How do we know that we say sodium chloride, sodium being first in chloride, and not chloride sodium? Because there's a list of rules. Chemical formulas list the most metallic elements first. So everything on the periodic table that's on the left side, remember there's a little stair step, that is a metal. Metals are named first. Now again, chemistry's fun. There are always exceptions to this rule, and we will cover them later. But in general, the metals are first. Compounds that do not include a metal, the more metal-like elements are listed first. So when we're dealing with nonmetals, how do we put the nonmetals in order? The ones that are closest to the metals towards the left are named first. Metals on the left side of the periodic table and nonmetals on the upper right. So remember, metals left, nonmetals right. Upper right, actually. Among nonmetals, those to the left are more metal-like. So here, if we name this, we have NO2, not O2N. Oxygen is after nitrogen on the periodic table. It's more right, so it comes after. It's not as metallic as nitrogen. And then NO, so you can see the difference here with, and these are, nitrogen is first because it's listed first on the periodic table. Oxygen is further on the right, so that's why it's not listed as this. Within a single column in a periodic table, so if we're going down a column, elements towards the bottom are more metal-like than elements in the top. So sulfur is right below oxygen, and it's going to be listed first because it's considered more metallic than oxygen. Also, there tends to be, when you're looking at compounds that have a metal and a nonmetal, the metals, they don't usually have as many as the nonmetals. So for instance, if I was to put a sodium here, let's say you'll have probably more of a sulfur and oxygen in the compound, and maybe one sodium for the two oxygens and one not sulfur. So, and hydrogens too. Hydrogens are nonmetals. Sometimes you'll have 4 of them, but you'll only have one metal. So they tend to have a little bit more number of them than the metals. So order to list the nonmetal elements in compound. So this is table 5.1. Anything over here is considered more metallic, and as you go this way, it's non-metallic. So if you have to list them in order when writing them out, this is how you were going to write them down. Oxygen and fluorine tend to be last. So even if you write one of these, oxygen is going to be written before fluorine because it's considered more metallic than fluorine. There's one exception here. Hydrogen is here. But when we talk about hydroxide, oxygen is first and then the hydrogen with the charge. This is a polyatomic ion. You need to memorize the polyatomic ions, which I'm going to get to, what those are. And yeah, you're not going to be able to just have a chart, because if we go back into person next semester and if you guys continue with chemistry, this is absolutely something you are expected to know. You will not be given a list, especially during the exam. How to represent compounds with polyatomic ions. Here are some examples of polyatomic ions. Polyatomic ions are a group of atoms that act as a whole unit. So where normally we deal with one element by itself, one atom, these are atoms joined together as a unit. You don't break them apart. They stay together as that unit. They are not usually nonmetals, and the overall, when you add everything up, which we haven't learned how to do yet, they have an overall charge to them. So they're an ion. Even though they're a nonmetal, they're a group, but they have an ion, either positive or negative, and they have different charged ions. So this is what we call polyatomic ions. You have in your chem handout a table. There's a lot of them. I suggest you start learning them because they will come up over and over. And if we transition back into person next semester or after that, this is something you will never be given. You are expected to know. What? Oh, I misspelled that word. Polyatomic ions appear. The formula is usually set off in parentheses with a subscript to indicate the number of that group when there's more than one. That's an exception when there's more than one. To determine the total number of each type of atom in a compound, we multiply the subscript outside the parentheses by the subscript for each atom. This may not make sense, but I'm going to show you. But in here's, I want to show you how to write them. So here is sulfate. It has a two negative charge. Sulfite, the 8 and the ite, we haven't covered naming yet, but the 8 means a compound with more oxygens than it's, think of like a twin or brother or sister. Ite means less oxygens. It has the same charge. This has 4 oxygens. This has 3 oxygens. 8 here. This means this is the compound that has the most oxygens for this. So how do we add these together? Well, in this case, we have aluminum, which has a 3 charge, which means it loses 3 electrons. So it's going to give, and we haven't covered this yet, I know, so some of this may be confusing. It's going to give those 3 electrons to the sulfate, but we put the sulfate in parentheses, and I actually forgot, this is incorrect. There should be a 2 right here. So make a mental note that this has a 2, and I forgot to write it out. This is in parentheses to let you know that this compound stays together, because if we didn't, you would have a 4 and a 3, and we don't write chemistry that way. When things start writing weird, put a parentheses. So what this means is that we have 1 aluminum atom, which should be 2 because there should be a 2 here, 3 sulfur, so this is what exactly it means here. You multiply the subscript outside the parentheses by what's inside the parentheses for each. So this means that we have 3 sulfur and we have 12 oxygen. So this compound in total, pretend there's a 2 here. There's 2 plus 3 is 5 plus 12, there's 17 atoms here. Now, here is potassium phosphate. I have a parenthesis here to allow you to see that this is one whole unit. But because there's only one unit, we remove the parentheses. So this is one of the things you're going to have to know, that this is a compound that is group. This is why you need to learn the polyatomic ions, because if you see this, you're going to think this is just potassium, phosphate, and oxygen. And it's not true. How would I know that this is not true? Because if you look at potassium, there's a 3 charge here. That is an indicator, not always, that this group is together. So here we have 3 plus 1 plus 4. This is 8. 8 atoms in this. Okay, so determine the number of each type of atom in magnesium nitrate. Nitrate is another polyatomic ion you'd have to know. These are all nonmetals, but it has a charge. 8 nitrate is, and it's not spelled here anywhere. Nitrate means this compound has the most oxygen, so nitrate has 3 oxygens. Nitrite has 2. But it still has a -1 charge. So how do we break this down? This means that we have 1 magnesium atom, we have 2 nitrogen atoms, and we have, so if we look here, we have the nitrogen as a group. Oh, let me jump back up. Sorry, I had to pause. 1 magnesium, we have 2 nitrogens, and 6 oxygens. So for a total here of 9 atoms. But in this group, we have to know how to separate them and what stays combined. So here we have parentheses because we have 2 nitrate groups for 1 magnesium. So magnesium has, nitrate has a -1 charge. So this is a 1 here as defaulted. And again, I know you guys don't understand what I'm saying about this crisscrossing I'm doing with the charges, but that'll come up. But when you put a compound together, you crisscross the charges. So magnesium loses 2 electrons, so that 2 comes onto this side. So we put the parentheses because the 2 is not on the outside. It represents the whole thing. So in this case, that's where the 2 nitrogens come from and the 6 oxygen. And then the magnesium. So the 1 is always implied. 1 magnesium atom and 1 nitrate group. But we have 2 of them. So this is 2 nitrate groups for every 1 magnesium ion. I hope I'm saying that right. Write a formula that represents the greatest total of number of atoms. So this is basically asking you to add up all these atoms and which formula, chemical formula, has the most combined atoms. So if we look here, I did the math for you, but you should check that you know how to do this. Add these up, make sure you get 23. Add this up, make sure you get 29. I broke this one down so you can see how to do this. 25, 23, and 20. So B has the most, but you definitely should be comfortable with knowing how to multiply within, because as we start doing these more, they can get more complicated. Because what if we put a number in front here? This is where students make mistakes. Chemical formulas. We have 2 types, and this is where some students have a hard time. We have an empirical formula and we have a molecular formula. And the easiest way that I can explain this is our bodies. We all have a skeleton. All of us. But what is on the outside makes us look different. So an empirical formula is the skeleton in the way that I try to state it. We all have a skeleton made of calcium and so forth. But molecular is the outer layer. That's what makes us look like us. So for example, molecular formula for hydrogen peroxide, molecular, that is the outer layer of what makes it look like what it is. It's H2O2. But the empirical, if we go into it and look at the skeleton, it's HO. So hydrogen peroxide looks like this, but it comes from building this as the foundation, as the skeleton. And a lot of compounds share the same empirical formula. It's what it is when it's in its molecular formula that it looks different and is different. The molecular formula is always a whole number multiple of the empirical. What that means is if we multiply this, we get this. So how do we do that? Well, we multiply it by 2 as a subscript, and that's when we get that. That's called a multiplier, that number that will multiply to get to the molecular. So for some compounds, though, they are in their empirical formula. For instance, water is. Why? Because we have whole number ratios. We only deal with whole numbers. If you cannot reduce every element or atom in the compound, it is at its lowest. We do not have fractions. So here's an example. Again, empirical is skeleton, but it's all whole numbers. We're not dealing with anything that's not whole numbers on a molecular or empirical side. So just for simplicity, whole numbers, skeleton, whole numbers, molecular. So here's empirical. This is the skeleton, but you can see the molecular. Now, many compounds have the same empirical, but when they're built out with a different number of a multiplier, which will multiply them, that's when you get your molecular. And this is the formula for it. Yes, we deal with subscripts, but to make it easier, we deal as an N like this, but you can put it as an N like this. You can solve for any of these. If you have two variables, you can solve for the third. So if you have the molecular and empirical, you can solve for N. If you have N and the empirical, you can solve for it. There's many things that we can do. And as you go into Chem 111, you will do them, and it gets a little bit more complicated. But it's the more familiar with it, the easier this becomes. So here is an example of a skeleton. All of these compounds share the same skeleton, but when the molecular is done, they all have different multipliers, and the multipliers give them the molecular formula. So in this case, this is on, say, you can solve for the 2. Once you know the 2, you take your empirical and you can get your molecular formula. Now, your book wants you to become familiar with different formulas and models. We use a lot of different models in chemistry. We have, if you were in person, you would have this ball and stick kit, and the balls are all different colors, and you can see even shapes. These colors are not random. They are associated with that element. So hydrogen is gray, carbon is black, nitrogen is blue, oxygen is red. So if you see compounds, they are going to match the color that is associated with that atom. So a structure formula uses lines to represent chemical bonds and shows how the atoms in the molecule are connected together. So it's just it sticks. Think of sticks, drawing shapes with sticks. Molecular models are 3D representations, so it tries to give you an idea of what it would look like in 3D, even though it's a flat surface. It's okay until you start using the stick and ball model, because then you can actually get an idea of what this looks like. So there's two different types of molecular models. There's the ball and stick. That's where the balls and the sticks, they have these little sticks, and you stick balls on the end of them, and that represents the colors. So they're connected, and you can build them into the molecule shape, and you actually see it in 3D how it looks. In space filling models, atoms fill the space between each other more closely to represent our best idea of how a molecule might appear if we scale it to visible size. So here is examples of all. So we have our chemical formula, or molecular formula here. We have our structural, which is just sticks. This is how, when we expand it out, how it looks. But when you try to do 3D, this is how it actually is 3D. And this is how it looks also like a 3D. It gives you a more depth to what you're looking at. And this being black is carbon. And we have gray, so we have 4 hydrogens. Here's water. Water has oxygen and hydrogen. So when you see this is not random. These colors are associated with that molecule. So the macroscopic world is basically everything big. What we can visually see, that's what's considered macroscopic. The atomic and molecular world are the particles that compose the matter, but we can't see them. So this is how we draw stuff to give us a representation, even though it's really a lot smaller than what we're even looking at, trying to understand the molecular world. The symbolic way that chemists represent the atomic and molecular world. So this is how we see things. We look at molecular, and then we start breaking it down in macroscopic, and then we look at it as molecular atomic to help us understand what we're looking at. So we're not just seeing solution in here, we're actually seeing millions and millions of water molecules that make up this water solution. So write a formula for the compound represented here. So this is not difficult. You count the balls. So, and then you figure out what balls these are. So this is oxygen, so 1 and 2. We have 2 oxygens, and we have 2 hydrogens. So we have 2 red and 2 white. This is hydrogen peroxide. Hydrogen is written first because it's more metallic than what would be oxygen.